Hello everyone, my name is Sahil Jadhav. I am a final year B.Tech student from Department of Cybersecurity at GHRCEM College of Engineering and Management, Pune. I, along with my teammate Ziya Al Hasan Mansuree, have developed a major project titled as Advanced Military Equipment Detection via Image Segmentation using Satellite Imagery, which is also called as AMED. This work was completed under the esteemed guidance of Professor Rupali Parte ma'am and with the constrained support of our HOD, Dr. Deepika Ajlakar ma'am, and the major project coordinator Rupali Parte ma'am.
So let's jump right into this. We're going to take a look at a really fascinating project today called AMED. Now, that's short for Adaptive Multi-Stage Ensemble, and it's a pretty advanced AI system that's designed to solve one of the biggest problems in modern intelligence. How do you find a specific piece of military gear from space? And just think about the scale of that for a second. We're talking about an area that could be 1 million square miles. That's just a sea of satellite photos. And somewhere in there, they're looking for a threat that might only be a few pixels wide. It is quite literally the ultimate needle in a haystack problem. And you know what? It's getting harder all the time. And this really gets to the heart of the issue. You see, we're facing two huge hurdles here. First, just the unbelievable amount of high-res satellite imagery coming in every single day. No team of humans could possibly keep up. And second, the AI tools we've been using for this kind of work, well, they have a critical and honestly a surprisingly simple flaw. Yeah, this really lays it all out. For people, it's a scale problem. It's too much. It's exhausting. For the AI, though, it's a strategy problem. You see, most object detection AI, they look for patterns in color and texture. But what's the whole point of military camouflage? It's to break up those exact patterns. So a simple coat of paint can make a billion-dollar weapon system completely invisible to a standard AI. But it actually gets worse. A lot of these advanced AI models are what we call black boxes. They might give you an answer, they might flag an object, but they can't tell you why. And in a field like this, where the stakes are incredibly high, getting an answer without the reasoning is a massive risk. You have to be able to trust and verify the machine's logic. It's not optional. So, how do you build an AI that can't be fooled by some paint and that actually shows its work? Well, this is where the AMED project comes into the picture. It's a completely different way of thinking about how to see and understand what's actually on the ground. And the name really tells you everything. Adaptive Multi-Stage Ensemble. So instead of trying to tackle this enormous, complicated problem with one single giant AI model, AMED breaks it all down. It creates this logical three-stage pipeline where each stage is a specialist at solving one small part of the problem. You know, the best way to think about it is like a team of detectives on a tough case. You don't just have one person trying to do everything at once. No, you have one specialist who finds the clues, another who analyzes those clues, and then you have the lead detective who puts it all together to crack the case. That, right there, is AMED in a nutshell. So, let's meet the team. We're going to walk through this whole three-stage investigation step by step and see exactly how they work together to find and then identify a target that's trying its best to stay hidden. Okay, so here's the lineup. It all starts with step 1, detection. This is handled by the spotter, whose whole job is to find potential targets. Then we move to step 2, segmentation, where the tracer comes in to create a perfect outline. And finally, step 3 is classification, where the detective analyzes that outline and makes the final identification. Let's break down how each one pulls it off. All right, first up, the spotter. This first stage uses a really powerful AI model to scan the image for anything that remotely looks like a vehicle. But here is the stroke of genius. It's not just looking for the vehicle itself, it's also trained to look for the vehicle's shadow. And why is that so smart? Well, you can camouflage a tank, but you can't camouflage its shadow. It's a law of physics, a dead giveaway that's almost impossible to hide. So once the spotter finds a vehicle and shadow combo, the case file gets passed to the tracer. Now, this stage has a very specific, very technical job. It takes that rough area the spotter found, and it creates a super precise, pixel perfect silhouette of the vehicle. It just cuts it out completely from all the visual noise, the ground, the trees, whatever's around it. And this is the aha moment. This is the whole point of the system. Because now that we have this clean silhouette, the detective can ask a much, much smarter question. A typical AI asks, what color is it? Which we know is easily fooled. The AMED detective asks, what shape is it? It completely ignores the camouflage and focuses on the one thing that can't be changed, the vehicle's fundamental geometry. And it's not just guessing either, it's performing a full geometric analysis. It's measuring the aspect ratio. Is it long and skinny or short and wide? It's checking the compactness. Is it more like a square or a rectangle? It even uses some pretty complex math to figure out what are called hue moments, which is basically like a unique geometric fingerprint for any shape. It's judging the vehicle by its bones, not by the clothes it's wearing. So that's a really clever strategy, right? But the big question is, does it actually work? Well, let's get to the good part, the results, and see how this digital detective team actually performs out in the wild. The first big number is accuracy. The system hits a 93.6% MAP score. Now, that's a standard way of measuring performance in AI object detection, but in simple terms, what it means is that it finds the right things and it almost never misidentifies the wrong things. It is incredibly reliable. And the second number is speed. The entire three-stage process, from spotter to detective, can chew through an image in just 50 milliseconds. To put that in perspective, that's about 20 frames per second. That is more than fast enough to analyze a live video feed coming from a satellite or a drone in real time. And if we geek out for just a second and look closer at stage one, we see two really important numbers. Precision is at 88.4%. That means when it says, hey, that's a vehicle, it's right about 88% of the time. Recall is at 87.1%, which means it successfully finds 87% of all the actual vehicles in an image. You want both of those numbers to be high and balanced, and these are really strong. And hey, remember that whole black box problem we talked about earlier? Well, AMED completely solves it with this. It spits out a simple dashboard that shows the original image, what the spotter found, the silhouette from the tracer, and the detective's final call. A human analyst can see every single step in the logic, which makes the whole thing transparent and, most importantly, trustworthy. Now, this project is way more than just a clever prototype. It is really laying the groundwork for a future with this kind of intelligent, transparent analysis can be used on a global scale. And the team isn't stopping here. The road ahead is pretty clear. The plan is to upgrade the tracer and detective stages into full-on deep learning models. They're even going to use other AIs to generate endless fake training images to teach the system new tricks. And from there, they'll expand beyond just what we can see and start pulling in thermal and radar data, making the system even more powerful. But the potential for this tech goes so far beyond just military work. I mean, think about it. This same shape-based approach could be used for so much good. You could track emergency vehicles during a natural disaster, monitor shipping traffic in ports to understand global supply chains. The applications are just enormous. And that really leaves us with one final, kind of mind-blowing question. Projects like AMED are really the first step toward a future where we might actually have the ability to analyze and understand our entire planet in real time. And if we could do that, what patterns would we see? What problems could we finally solve?
Hi. So I'm showing my implementation right now. So this is the main.py. In this we have used hue algorithms and various types of algorithms. And now I'll show you the GUI. Yeah. So this is the GUI to operate the main.py and its algorithmic features and the model I've trained. So in the first dashboard, I'll load an image. So yeah, firstly I'll load image. Uh, this one. I'll set a threshold. Run it. So yeah, this is the original image, and this is the stage one, which is the bounding box detection. And there's one more vehicle in the background, which is also been detected. And here is the two maskers masks of both of the uh, vehicles which have been captured in the segmentation layer. Segmentation layer itself defines the vehicle pixel is 33626 px and shadow is 3196 px. The second marks, which is the smaller one, the vehicle and shadow pixel size are here. And in the classification layer, it has classified it as a military vehicle with a confidence rate of 0.65. And the other one, I can see it, but I'll tell you. The other one is also a military vehicle, which with the confidence threshold of 0.65. And here we have the summary of the complete pipeline. Total vehicle detected are 2. Processing time was 430 milliseconds, and it is a meta timestamp. And detection cases were 2 military vehicles. Here also you can see that. And for now, I'll export the images. The images has been exported with the name of these. So I'll find it in my results output. Uh, yeah, here are the images. I'm sorry. Yeah, and you can export it also. And here are the log. And you can see the whole implementation structure here. Here's the Unity file. Here was the whole Unity file in which we included the terrains for the synthetic data we trained. And here is the model. So you, this is our model, and this is our model's results. So yeah.